This is the first FRQ on the work energy review packet. It says that we have a ski lift carrying skiers along 600-meter slope inclined at 30. To lift a single rider is necessary to move 70 kilograms of mass. This is assumed to be the mass of the skier and all of their gear to the top of the lift. Under maximum load conditions, 6 riders per minute arrive at the top, which is not pretty fast. If you're a skier, you expect it to be better than that. And if 60% of the energy is supplied by the motor going to overcome friction, what power does the motor need to supply? So then there's this kind of efficiency question here at the end. Let's start by recognizing, for starters, that we need to move a skier from the kind of ground level at point A up to the top of the hill at point B. So, that's kind of one way of approaching the problem, is recognizing that it's going to be an energy question. The amount of gravitational potential energy is going to change. It's 0 at A, and it's not 0 at B. And power, by definition, is the rate at which work is done. So I could write it as work over time. And we know that work is the same thing as a change in energy. So whatever gravitational potential energy has changed, I can divide it by the amount of time it takes to do that in seconds, and I'll have the answer to my problem. So I need to first answer, well, how much did the energy change? Well, let's do this. Let's acknowledge then that the gravitational potential energy has changed, and it's going to be UG final minus UG initial. Now, the initial gravitational potential energy is 0, and so therefore it's just going to be equal to mgh times 6. mgh times the 6 riders, where mgh is the gravitational potential energy for one of the riders. And the height here is something that we can use right triangle trigonometry to figure out. I have 30 and 600 meters, so it's going to be sine 30 times 600. The height here is 300 meters. Again, I'm just using some right triangle math to figure that out. So I know h, I know m, that's 70, right? So I'm going to write in 70 kilograms, and g is 9.8 meters per second. And the height, we just figured out, it's 300 meters. And I need to multiply the whole thing by 6. And that's going to be equal to the change in energy of all of the riders. And when I do that, I get 1,234,800 joules. Now, you could round that if you wanted to, but that's the change in energy in the system. And if I look back at when I started this problem, I recognized that now that I know that, I just have to divide it by the total amount of time. Well, it takes 60 seconds for that to happen. So, one approach is to say, all right, well, let's find the power that is required to do that. And, I'm going to divide the energy by the time. That's going to be, I can write this out in scientific notation, 1.23 times 10 to the 6th joules, if I wanted to put that into scientific notation. And the denominator is just going to be 60 seconds. Let's remember that a joule per second is equivalent to a watt. That's going to be 20,580, roughly, depending on how you round it. It's going to be around 20,000 watts, or 20 kilowatts, 20,580. So here's the thing, that if the motor was perfectly efficient, there was no friction, we'd be done. The kind of question is over with. But there's a couple of different ways to approach this. 40%, it's only 40% efficient. So, we could think of efficiency as, the output power over the input power. That's kind of one way of thinking about efficiency. It's just more generically output over input. So if you put, 10 units in, and you get 5 units out, the efficiency is only 50%. So if 60% is going into overcoming friction, that means that our efficiency number here is only 0.4. Oops, 0.4. The output power is what we need. That's 20,580. That's ultimately what we have to deliver to this system. So the question is, well, what does the power of this motor need to be? Well, it's going to have to be bigger than 20,000. Um, and so now we can see that if we're solving for the input power, we're going to have to take the output power and divide it by 0.4. And we're going to get 51,450. So therefore, the input power, this is our final answer, ends up being around 51 kilowatts. And again, this is just, depending on how you round it, I'll leave it to 2 sig figs in this case. 51 kilowatts.